Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Welcome to the Deep Dive. Today our focus is razor sharp. We are taking a deep dive into the attitude indicator.
The AI.
The AI, right? Or as pretty much every student pilot knows it, the artificial horizon. For anyone working towards their license, this isn't just another dial on the panel.
Oh, not at all. It's arguably the single most important instrument for maintaining control, especially, when your external visual references just disappear.
It's the truth machine in the cockpit, really.
It is. Our sources all confirm that the AI is, it's recognized as the most realistic and reliable instrument you have available. And that's because it gives you this immediate continuous read on where your aircraft is pointed relative to the world outside.
Instantaneous.
Instantaneous. If you're learning to fly, this instrument basically translates the complex three-dimensional movements of flight into a simple two-dimensional picture that you can trust.
Okay, so let's get into the mechanics of that picture.
Right.
Our source material, it highlights that the AI provides an instantaneous indication of even the smallest changes in attitude. That speed is just so crucial.
It is.
If you think about the lag you get in some of the other instruments, the AI is always ahead of the game. So our mission today is to unpack the physics that allows it to be so fast and so trustworthy, and then translate all that theory into practical cockpit application for you, the student pilot.
Right, and the context for its importance is, it's simple. It visualizes the aircraft's pitch, is the nose up or down, and its bank or roll.
How does it do that?
It does that by contrasting a little miniature aircraft symbol against a horizon bar. And what makes it so unique is that its indications are described as, and I'm quoting here, very close approximations of the actual attitude of the aircraft. It's designed to defeat disorientation.
So let's start right there with the display itself. When you look at the instrument panel, you see the AI. What are those two main players doing? We have the miniature aircraft, which usually stays fixed, and then the horizon bar, which is the part that moves.
Exactly. The miniature aircraft is stationary, but it perfectly mimics your aircraft. So if the nose of your plane pitches up, the nose of the miniature aircraft on the dial appears to pitch up relative to that moving horizon bar.
So that brings us to the fundamental principle.
It does. The relationship of the miniature aircraft to the horizon bar is designed to be identical to the relationship of the real aircraft to the actual horizon outside.
It's a simulation, but a perfectly engineered one. Okay, so the horizon bar, you said it moves, but it's not moving randomly. It represents the true horizon. What defines that true horizon, and how does the instrument make sure that bar stays horizontal no matter what we're doing with the plane?
That's where the physics gets really fascinating. The horizon bar needs to stay stable in what's called a horizontal plane. That gives you that reliable reference point.
Mm-hmm.
And this stability allows you, the pilot, to visualize attitude changes relative to that true horizon as the aircraft pitches around its lateral axis.
That's the imaginary line from wingtip to wingtip controlling pitch.
Right. Or as it banks around its longitudinal axis.
Nose to tail, controlling roll.
Exactly.
Okay, here's where it gets really interesting for me. How does the internal mechanism resist all the forces acting on the aircraft? I mean, we could be in a steep climb or a sharp turn, and yet that little horizon bar stays perfectly fixed.
Yeah.
It's all about the gyro inside, right?
Absolutely. The entire reliability of the AI rests on this physical principle called rigidity in space.
Rigidity in space.
Inside, there's a small, heavy wheel, a disc mounted in a horizontal plane and spun at a very high speed. It's usually powered by a vacuum system or electricity. The faster it spins, the more rigid it becomes.
We've talked about this with other instruments, but let's make this really concrete for our listener.
Yeah.
If you've ever played with a toy spinning top or, even just watched someone ride a bicycle, you've seen this exact physics in action.
That's the perfect analogy. Think about a spinning bicycle wheel. When the bike is stopped, the wheel just falls over.
Right, instantly.
But when that wheel is spinning really fast, you can lean the bike over, you can tilt it, and the wheel fights to stay upright and maintain its original plane of rotation. That opposition to change is rigidity in space.
So if we apply that to the cockpit, the spinning gyro is like that incredibly stable bicycle wheel. And the aircraft, which is basically bolted around the gyro, is just the frame of the bicycle.
Precisely. The magic here, if we connect this to the bigger picture, is that the aircraft actually rotates around the spinning gyro.
That's the key.
That is the key. The gyro maintains its fixed position relative to true space, the actual Earth's horizon, and the instrument case, along with the aircraft, it just moves around that stable core. This is why you trust it implicitly. It's governed by predictable physics, not temporary forces or gravity pulling on some kind of pendulum.
Okay, so that transition from the theory, the reliability, to the practical setup is just so critical.
Yeah.
Because if the gyro is inherently reliable, the main source of error often comes down to us, to the human setup.
That's right.
Moving from theory into the cockpit, we have to set this super stable instrument up correctly for the flight.
We do. And a student pilot needs to know how to perform this alignment. You can't just hop in and assume it's set perfectly. Every AI has an adjustment knob, usually at the bottom of the case.
And you use that knob to do what exactly?
You use that knob to move the miniature aircraft symbol up or down.
And what are we trying to achieve with that adjustment?
You're establishing the baseline for straight and level flight. The standard alignment is to adjust the miniature aircraft so its little wings perfectly overlap the horizon bar when the aircraft is actually flying in straight and level cruising flight. That is your zero reference point for pitch.
So why is this so important? I mean, if you forget to align it, or maybe it's misaligned from the last flight, what's the actual danger?
The danger is a high workload and chasing a false indication. Just imagine you're cruising perfectly level, but the little airplane on the instrument is set 3 degrees nose up. You now have a perceived pitch indication that you're climbing slightly. Your instinct is going to be to push the yoke forward, thinking you need to level out.
Right. You'd be flying the instrument, not the plane.
And you'd inadvertently be pushing the nose down, maybe increasing your speed or even descending, all because you're flying by a false picture. Correct alignment is just essential for reducing your cognitive load in the cockpit. It prevents these self-induced errors.
That makes the setup procedure way more than a formality. It's a critical safety check. But what about the instrument's mechanical limits? We know the gyro is rigid, but it can't maintain that perfect plane if the aircraft does something really extreme.
No, it can't. And this raises a really important point for students, especially as they get into more advanced maneuvers. These gyroscopic instruments use gimbals, a series of rings that let the gyro spin freely. But those gimbals have physical stops. They can only rotate so far before they hit the frame.
And what are the typical limits before we hit those stops?
It varies by model, of course, but the banking limits are pretty generous, usually between 100 and 110 degrees of bank.
That's a lot.
It is. Pitch limits, though, are tighter, generally 60 to 70 degrees up or down. Now, these are generous for normal flight, but if a student performs an overly aggressive maneuver, they can be exceeded pretty easily.
And if those limits are exceeded, the instrument will, as the books say, tumble or spill. For a student pilot, what does that actually look like in the cockpit?
Well, in the traditional vacuum-driven instruments, tumbling and spilling are basically the same failure mode. The gyro hits the physical limits of the gimbals. When that gimbal hits the stop, the gyro is forced out of its horizontal plane.
So what does the pilot see?
To the pilot, the horizon bar doesn't just go blank. It goes wildly erratic. It'll swing violently. It'll show extreme pitch and bank angles that the aircraft isn't actually doing, or it might just settle into some useless steep indication.
I can just imagine the sheer panic of seeing that happen for the first time, especially during intense training. It's like your anchor just flew away.
Exactly. And once it tumbles, the instrument gives you incorrect, totally unreliable indications until it slowly realigns itself. And that process can take several minutes. Until it recovers, you have lost your primary attitude reference.
That's terrifying.
It is, but it's worth noting, as the source material points out, that many modern digitally driven or electric attitude indicators, they often use complex electronic filtering or different mechanical designs to prevent this physical tumbling. And that's a major safety enhancement for today's students.
That's a great distinction to make. Okay, now let's pivot to a point of persistent confusion for student pilots, whether they're flying new or old equipment.
Yeah.
Interpreting the banking scale.
Yes.
This is that scale with the tick marks running across the top of the instrument face.
It causes trouble because of a really subtle directional conflict. If you look at most modern training aircraft, the banking scale indicators, usually a little triangle or an index market, moves in the same direction as the aircraft is actually banked.
So if you bank 30 degrees to the left, the indicator moves to the 30-degree mark on the left. That feels intuitive.
It does. But, as our sources warn, not all instruments follow this rule.
Why is there a contradiction?
Some older designs, or just designs from different manufacturers, they occasionally move in the opposite direction from the bank. If you bank left, the indicator actually moves to the right.
Okay, why would they do that?
It was sometimes done for engineering reasons related to the display mechanism, or maybe just a different design philosophy, maybe aiming to represent the ground rushing up to meet you.
So if a student pilot encounters one of these reverse scales, or maybe they just transition between two different aircraft models, this could completely confuse them if they're relying on that indicator to figure out the direction of the bank.
And this brings us to the most critical takeaway for this entire section.
Okay.
The banking scale should never be your primary indicator for the direction of the bank. Because of these potential contradictions, that scale has one and only one primary purpose.
And that purpose is?
It should be used only to control the degree of a desired bank. It's a precise measurement tool. If your instructor tells you to maintain a 30-degree bank turn, you look at that scale to make sure the indicator is holding steady on the 30-degree mark. It helps you avoid overbanking or underbanking.
So we use the scale for measurement, for the number. But the definitive answer for the direction of the turn has to come back to that core visual display, the fundamental relationship we talked about earlier.
Absolutely. The direction of the bank must be determined by the relationship of the miniature aircraft to the horizon bar. If the miniature aircraft's left wing dips below the horizon bar, you are banking left. If the right wing dips, you are banking right. That visual picture is governed by the unchanging physics of the gyro, which is why it's reliable no matter what the banking scale is doing.
So always trust the picture over the scale for direction.
Always.
That simple distinction, scale for degree, picture for direction, that's the difference between a smooth instrument scan and a pilot who's fighting an instrument that's confusing them. It saves time, it saves mental energy, which, as a student pilot, is always in short supply.
It's the absolute foundation of instrument proficiency. You have to develop the habit of looking past the auxiliary info and focusing on that core relationship.
We've covered a lot of ground today, from the high-level physics down to the nuts and bolts of pre-flight setup. So you now understand the AI speed, the beautiful simplicity of rigidity in space that locks that horizon bar into reality, the necessity of correct adjustment to set your zero-pitch reference, and that critical rule for using the banking scale only for the degree of bank, never the direction.
And remember that the AI is the most realistic instrument precisely because it is governed by predictable physics. It ignores temporary accelerations, it ignores maneuvering forces, and it sticks firmly to the true horizon. It is your ultimate reference point when nothing else makes sense.
It truly is your anchor.
It is. So consider this as you progress through your training and you start encountering different weather or night conditions. In poor visibility or flying over water or featureless terrain at night, the visual horizon can be slanted, it can be confusing, or it might be entirely absent. In those conditions, the AI gives you a flawless, true horizon. So what stands out to you about relying entirely on a spinning mechanical gyro over your own eyes and your vestibular sense, your inner ear system for balance in a dark or adverse environment? That reliance on physics over biology is something fundamental to mull over as you prepare for your next flight lesson.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.